Just to make the explanation regarding the hash arrays and Bloom filters more clearer, I'm showing the RTL implementation here. So the partial Bloom filter that we discussed is nothing but a dual port memory block that you can see here, right? So that is 1 bit wide and 4096 in depth. So that is fixed for all the blocks. So as we saw in the slides, let's talk about the 3 byte Bloom filter, right? So for recognizing 3 byte windows patterns, I mean, right? So we looked at the partial Bloom filter. Partial Bloom filter will be same for all the blocks basically, whether it's 4 bytes, 5 bytes and stuff. So only thing that happens is that as you go on increasing, so as you go on to 7 bytes and stuff, so you cannot fit in a lot of signatures basically in the same hash array. You will get a lot of false positive rates, right? So we would want to keep it below 10%. So that is the thing. So that is the thing about partial Bloom filter. Now this is the hash array. So this basically takes the input x. So as you can see that 3 byte window that we talked about, so that it takes, and then it takes the di, right? So it's a set of 24 12-bit data basically. So that is the thing. So from here d0 to d23, right? So that is stored here, right? So for example, this is for generating h0 hash 0. So this is the set of 12-bit integers we have chosen. So these are chosen at random, okay, to ensure that the uniformity of the function is preserved, right? So this is for generating h1. So and this will be used for calculating h2, sorry, and then this is h for h3, and then this is for h4, and then this is for h5, right? So you can see those values are hard coded here. So before that so we'll instantiate these hash arrays here. At that time I'm hard coding them, so I'll talk about that a little later. But assume for now I'm already getting these d values, that is the 12-bit values as input, right? So how are we calculating the intermediate variables? That is the multiplication, right? So as I mentioned earlier, we can use a mux. So as you can see here, depending on the 0th bit of x, so if it's 0, I can directly assign it to 0, right? The output, right? Or else I can just if it's 1, I can just directly pass away d0. So that's how I'm doing multiplication. I figured out this is much more efficient to do. Another possible optimization is to use AND gates and stuff, so that is there, but since we had scarcity of time, we couldn't do that, right? And then I'm talking about stage registers here. The first I'm calculating the multiplication intermediates, right? So that I'm doing, and after that, at the second stage, I am doing the XOR operation of all of those, right? 24 values, right? So that is going to give my hash value, right? For example, if I'm using x and d0, this will be hash 0, h0, and if I'm using x and let's say d1, so this will be h1 and so on, right? So that is calculated here, right? So each Bloom filter is since it's a dual port memory, I'm taking inputs from 2 hashes to check if the if to check for the presence of pattern basically, like after the training phase, right? So you can see hash array a0 and a1. So I'm hard coding these values that are that is the 24 number of 12-bit values that I'm hard coding here, right? So that is there, and then I'm giving the h0 h1 here, and that is I'm getting r0 r1 here. I'm again using that in a pipeline to get the match here, right? So the match is true only if all of those values are true. That means I take an input and then I hash, with different functions, and then I find one nut, all of the locations pointed to by them in different Bloom filters. If that is true, then that's definitely a match. So before that, obviously it goes through a phase of training, right? So for that, what we did was we basically loaded the coefficient file itself to the memory based on whatever rules we wanted to support, from the snort. We Based on those, we wrote a Python script to calculate the hash values and the corresponding coefficient file for that. And so for example, you can see these, it's mostly zero, some of, I think somewhere, it's very hard to see, but you will get ones. So that is basically how we did it, and then we initialize that so that we don't need to train the Bloom filter, right? So when we initialize it, it's already trained using coefficient files, right? And then from that, so that is there. And then these are the byte offset shifters, right? So for example, I'm instantiating all of them with byte offset of the words. So you can see the first 4 bytes, the first 3 bytes I'm just giving it to the first one. Next I'm shifting it by 1 byte, and so on. And next word also comes into picture, right, to accommodate for all the possibilities. And then if any of them is 1, then the match is there, right? So we ran the simulation, and then one of the bits for which we had trained, are this thing, Bloom filter. So that is 64 right? So that is the DLL. So if we send that in the input, we can notice the match is enabled here. And then we are giving another interface called match, that goes on to the processor block. So that will be high, if we found a match for the entire section of the word, the output, right? Sorry, the packet, right? So I wanted it specifically like that because in the processor stage, I had built a finite state machine where in the execution, after the execution stage, right before the execution stage, the matcher gets stored to the one of the register files in the processor, so that to enable processing basically. So that's why I want it high all the way around, so I mean throughout the way. So that's the thing. But here I'm sending some input without any pattern, right? So let's see what that does. I think this should be enough. Yeah, you can see out data and out control we're getting here, but there is no match, right? So that is how kind of how it works.